Okay, hello everyone. I am Nguyễn Quang Minh. I am the leader of the group before, and our uh, project is about the operating a principle of semiconductor memory and structure and operation of the different type RAM program. So this is my email, and my I will talk about the semiconductor memory and the operation of it. So first of all, we need to understand the overview of semiconductor memory. So, similarly, it serves as the primary memory component in a microcomputer-based system and is utilized for the storage of both program and data. The primary memory component are semiconductor devices that serve as permanent storage of code and data. The microprocessor and can access the semiconductor memory directly. This is crucial to ensure the synchronization between the retrieval speed of information stored in the main memory and the processing time of the microprocessor. Semiconductor devices are the preferred choice for primary memory. The operation of semiconductor memory. So the memory chips memory cells are arranged in an arranged configuration, with each individual cell having the capacities to store a single bit of data. Please refer to the diagram presented below in order to comprehend the internal structure of memory. The diagram is the This below illustrates the memory circuit comprising 16 watts denotes as W0 through W15, with each watt possessing a length of 8 bits represented as B0 to through B7. The memory cells within a given row or watt are linked through a shared pathway known as a word line. Conversely, the send or write crucial establish a connection between the scene write circuit and the memory cell within a column through a pair of group bit lines. Moreover, the circle responsible for sensing and writing is linked to the line designed for both input and output of the data. And you guys can see in the picture this is the organization of the memory cell on a semiconductor memory chip. So here is the memory cells from B0 and through B7, and this A0, A1, A2, A3 is the address decoder. Is the W0 through the W15, and those are the send-write circuit for each um, column of B. And from here and here, it will be the data input and output lines. So next we will talk about the type of the semiconductor memory. So random access memory can categorize into two distinct types, namely semiconductor memory and read-only memory. Semiconductor memory, or we can call that RAM, and read-only memory can on ROM. So we talk about the RAM. So first is the static RAM. The static random Shared memory, or we can call it SRAM, is a particular kind of memory where the data stored in each memory cell remain constant as long as there is a continuous power supply to the memory chip. However, if there is an interruption in the power supply, the information stored in the memory cells data can be lost. Once power is restored to the memory chip, there is no assurance that the memory cell will retain the same content as before the power interruption. This characteristic of static RAM being violate is attributed to the behavior. Due to their quick accessibility, static RAM cells are considered to be faster, complementary metal sheet semiconductor, or we can just see most SRAMs are characterized by their low power consumption, as power only supply the cell when they are being accessed. The second is the dynamic RAM. Static RAM is faster but require many transistors, making it more expensive, more price, and we need to similar cell to develop a cheaper, higher and higher density RAM. So the simpler cell hold data only until it is read and or write. Often dynamic RAMs are used simple cells. So the capacity to store data in dynamic RAM memory cell to store the content for longer. The capacitor must be fully charged. The process of charging the capacitor occurs during the act of reading or writing, effectively refreshing the substance within the cell. After charging, the capacitor consumes equal ampere of current while renewing its content before the cell is charged. You can recover the right information. And third is the electrical iterable programmable ROM, or we can call it EEPROM. The electrical programmable, erasable, or and readable nature of the EEPROM presents a challenge due to the need of distant voltage for each operation, thereby adding complexity to the circuit. However, despite this added complexity, the numerous benefits offered by EEPROM can surpass the circuit in chassis. And final is flash memory. EEPROM like flash memory erase electrically. Flash memory can selectively erase ions, while cell flash memory write a block of cell once, and flash memory also write, erase, and read at the same power, at the same voltage. This simplifies the circuit and save hours.
Okay, so today I'm gonna talk about the structure of static graph. So the following show a basic structure of a 1-bit SRAM memory cell. So here's a memory cell is the smallest group of components that can hold 1 bit of data. So from the image is by appearing somewhat complicated. The circuit is merely a cross-coupled inverter with two paths transistor. The breakdown of the inverter with NMOS and PMOS transistor is shown in the following image. So this circuit is a little simpler to comprehend. So in the inverter, the two PMOS transistor serve a pull-up and the two NMOS transistor serve as a pull-down. So early SRAM implementation include all 6 transistor, 60 for in cross-couple inverter and 2-pass transistor. However, more widely used design use polysilicon load resistor as pull-up rather than a PMOS transistor because the load resistor would have high resistance are made out of a polysilicon layer on top of the transistor. The memory cell size were greatly lower as a result. So there are a few other extra memory cell design and one substituted polysilicon PMOS for the huge polyroad resistor, which had to be slightly larger to deal with the leakage current. The benefit of this design include the ability to construct them with a poly PMOS layer on top of the NMOS layer and the fact that they have overall better characteristics than their polyroad resistor counterpart. So the complexity of adding a layer on top of ordinary silicon increased as the amount of cache incorporated within the CPU die increased. A 4 transistor design without a pull-up load was the end result. The memory cell size was greatly decreased because there was just a 4 transistor, but designer had to pay special attention to liquid current. So due to the complexity of the polyload layer, 60 extra memory cells is still the most commonly used design from a fabrication standpoint. The term CPU cache memory may be familiar to you. Actually, the memory is a type of SRAM that includes the CPU die. So let's talk about the memory recycle. So the timing diagram of recycle is shown here in the figure 1 and applying the address signal start at the read cycle which read data from memory. The valid address must be kept constant for predetermined amount of time for the read cycle time following the activation of the CS and OE signal. The generate data start to emerge on the data line after a delay of TGQ. So the output enable access time is measured with regard to the high to low transition of the OE signal. So the address access time or TAQ is the amount of time that elapsed between the time that a valid address first appear on the address line and the time that valid data first arrive on the data line. The time TEQ measures the chip enable access time or the amount of time it takes for valid data to appear once the chip select signal CS switch from high to low. So here is the figure and timing diagram of this cycle. So for the memory write cycle. So the timing diagram of the write cycle is shown in the figure 2. So applying the address signal start the write cycle, which is used to write data from memory. The valid address must be kept constant for predetermined amount of time or write cycle time. The CS and WE signal are then turned on after a minimal amount of time, A, which calculated from the start of the valid address. The write enable signal WE is enabled. The write push wide is the length of time. The the WE signal is active. The data that need to be written in the memory at the specific location is applied to the data line after WE signal is active. After data is applied at the data input lines, the WE signal must continue to function and must do so for at least the WD. So after WE signal is turned off, the data must still be valid for a period of time for the whole time. This is the figure of a timing diagram of a life cycle.
DRAM overview. DRAM, known as Dynamic Random Access Memory, is a specialized form of memory that employs individual
capacitor within an integrated circuit to store data bits. This type of memory find widespread uses in personal computer, workstation, smartphone, tablet, and digital camera, among various other electronic devices. Notably, DRAM possesses a volatile nature, necessitating a continuous power supply to retain stored data. In instance where power is disconnected, the data stored in DRAM is irretrievably lost. Additionally, it's worth mentioning that DRAM operates at a com- comparatively slower pace when compared to alternative memory options like SRAM and ROM. Such structure of DRAM memory. One we focus on 1-bit memory structure of DRAM. DRAM cell consists of four elements: the capacitor, the transistor, the word line, and the bit line. The figure 1 describes the DRAM cell, bit line, word line, transistor, and capacitor. And we discuss about how does DRAM work. The utilization of a transistor is employed in the process of either charging or discharging the capacitor whenever they need to store a bit within the memory. Charging the capacitor signifies a logic high or 1, while discharging is signify a logic low or 0. Figure 2 illustrates the presence of the word line and bit line, which serves the purpose of facilitate facilitating the charging and discharging action. The word line gets high during a read or write, which causes the transistor to link the capacitor to the bit line. Any number 1 or 0 on the bit line is saved or retrieved from the capacitor. Since the charge on a capacitor is too tiny to be read directly, a circuit known as a sense amplifier is used to measure it. The sensing amplifier outputs the corresponding logic level after detecting the minute variation in charge. The charge must flow out of the capacitor in order to read from the bit line. Read and hence harmful in DRAM. To circumvent this, the value received from the bit line is pre-charged back into the capacitor via a process called pre-charging. Equally problematic is the fact that the capacitor lacks charge over time. Therefore, to maintain the data stored in memory, the capacitor must be refreshed periodically. Refreshing works just like read and ensure data is never lost. This is where DRAM gets the dynamic moniker from the charge on a DRAM cell that is dynamically refreshed every so often. The next section is DRAM memory organization. The first is memory array. The simplest way to organize is mount more cells on a bit line as shown in the figure below. In actual manufacturing, we will not hang cells on bit line indefinitely by adding more cells to the bit line. The length of the bit line will be longer, which means the capacitance of the bit line will be higher, which in turn will reduce the signal edge rate on the bit line, level of high, low, and high. In the long run, this will lead to performance degradation. As a result, we should limit the total number of cells attached to a bit line and attract more cells to other bit lines. According to cell structure diagram, the bit lines in a cell structure are equivalent in function. In this way, we can reduce bit line length by allocating cells to different bit lines. As a result, cells are organized as follows. Figure 4 describes the length of the bit line can be reduced. In order to expand further, you must increase the bitline size. If there are enough cells connected to the board bitline, after increasing the bitline, the structure below can be seen in the figure 5. The diagram shows that when a bitline is added to the memory array, the number of sense amplifier with large and right driver also increase, leading to an increase in cost, power consumption, and chip size. Therefore, increasing the number of cells attached to the bitline is preferred over increasing the number of bitline. This results in a higher number of word lines compared to bitline in the memory array. The figure displays a memory array consisting of 16 cells with 8 word lines, 2 CSL, and 2 WES. For control signal, it can read and write 1 bit at a time, representing an 8 times 2 times 1 memory array. If the 2 CSL and 2 WEs are combined into 1 CSL and 1 WE, as shown in the subsequent figure, the memory array will have 8 word lines, 1 CSL and 1 WE, allowing it to read and write 2 bits at a time. This results in an 8 times 1 times 2 memory array. Here is a 8 times 1 times 2 memory array. According to the above process, continuously increase the number of cells, and finally you can get a M times N times W, which means row times column times data width memory array, as shown in the figure below. Figure 7. Among them, M is the number of word lines, N is the number of CSL and WE control signal, and W is the bits that can be read and written on. The next section is data width. The number of bits accessed during read and write operation of the memory array is referred to as data width. The arrangement of CSL and WE control line affects the number of bits. Row in DRAM memory, row and word line have a 1-to-1 relationship, and a row is essentially its own cell connected to a single word line, as illustrated in the image below. Selecting a row while reading or writing data in DRAM open cell controls the word line associated with that row and cache and data in the cell for use by sense amplifier. Row size. The quantity of cells in a row determines its size. 1 bit of data is saved in Excel, hence the row size is the total number of bits contained in each row. Column. In a memory array, a column is the smallest accessible unit. N equals row size divided by data width, where N equals the number of columns in a row. The illustration below shows a column with a row size of 32 and a data width of 8. Figure 10. Column size. The size of a column is equal to the data width and is determined by the number of cells it contains. The layout of CSL and WE control line is also connected to a column size and data width, which is fundamentally equivalent. Memory bank. Word line will become longer and longer when more and more bit lines are added to them, which will result in longer bit lines, more cells tied to them, slower add rate, and worse performance. A memory array can thus be enlarged infinitely. DRAM is intended to stack numerous memory arrays together in order to further enhance capacity without sacrificing performance, as seen in the accompanying figure 11. Row, column, and data width are the same for every memory array, which is referred to as a bank. For data read and write operation during DRAM data access, only one bank will be enabled. Now we will discuss read and write cycle of DRAM memory. And we will introduce some information relating about how to read or write to a specific cell in an array. The red cell in the following image has a value of 1, whereas the blue cell has a value of 0. A memory location can only be located via a memory address. The row line decoder is connected to line 3 of the address bus, which also feeds a group known as the row address buffer. This procedure makes it possible to identify column address. The last 3 lines link to the column marked and demarked after feeding the column and address buffer. This procedure makes it possible to identify column address. Memory address multiplexing, which allows for the independent entry of row and column address, allows the memory module to have fewer external pins than necessary when additional addressing is needed for larger memories. It is vital to lower the number of pins. In this situation, the 6-bit memory address may be reduced to 3 bits. Power different control signal as well as memory location and data must be sent via external pins. For instance, each buffer needs extra pins like RAS and CAS. Column address stroke stands for CAS and row address stroke for RAS. Stroke refers to a signal that is used to designate an address while accessing DRAM in this context. In general, DRAM spot both row and column address and split the row address bus into 2 halves. Currently, CIS is a signal that is sent to validate the column address, and RAS is a signal that sent to DRAM to tell it of the pertinent row address. DRAM data bits are kept in single cells that situated where the row and column address converge. Read operation. The following sequence presents the read operation procedure. The memory control applies the row address of the address pins. RAS is activated and the bit line is recharged by about half of the voltage provided to the DRAM module. An active low signal is a RAS. The decoder now utilizes a 3-bit memory address to choose one of the 8 potential output once the bit line had been detected at the attack from the preload circuit. As a result, a voltage is applied to the proper word line, and the send amplifier sends the value of the entire row using the capacitor charging or discharging technique described before. The data that the memory cell originally contained is lost during the destructive operation, but the raw original content are safely retained. Note: the column address is stored on the address pin. The column address buffer is large, and the column must utilize the column address to choose the proper output from one of the send arms when the CIS signal is triggered. The binary number being sent to the data buffer is what we are interested in. The output is accessible on the external data pin when RAS is deactivated. Update the row with the send arm data. CIS is turned off. The word line goes away, and the output data is lost. The bit line is charged in advance of subsequent cycle. Read cycle. A basic read cycle can be explained with the following diagram. After a little propagation delay, the row address is initially displayed in the external address box, and the RAS signal is enabled. After a little transmission delay, the column address of the external pin is solved and the CIS signal is enabled. Available output data when RAS signal is deactivated until CIS is turned off accessible. Write operation. The writing process follows a similar pattern to reading. Let's imagine, for instance, that we wish to enter the binary number 1 in cell that already has the binary value 0. The memory controller applies the correct row address to the array pin after pre-charging the bit line. One of the word line is then used to decode and activate the address pin. The input data is then placed on the data line and the write enable signal is turned on after the sensing arm headlights the outline value. Now that the column address is sound in the address pin, the timer is activated, loading the new value into the relevant sense arm in accordance with the column address. After that, the row is updated as before but with the new data. Following that, CIS and RAS are both turned up and the bit line is pre-charged for the subsequent cycle. Write cycle. This diagram may be used to represent a 1-bit DRAM write cycle. The row address is chopped after being initially presented as the external address pin. The input data is made available while the write enable signal is applied and the column address is sound as a pin. Now the column address is chopped. Then the write enable is turned off and input no longer accepted. Finally, the row address and the column address chop are disabled. The last thing is refresh DRAM. 1. What is DRAM refresh? Memory refresh is a process that largely defines the characteristic of dynamic random access memory, as known as DRAM, which is the most used computer memory type. The process involves a periodic reading of information from a certain section of the memory and the immediate rewriting of the read information to the very same area without making any change. When in operation, each of memory cell needs to be refreshed repeatedly. However, the maximum interval between two refreshes is defined by the manufacturer of the memory and lies in the millisecond segment. Why does DRAM need to be refreshed? DRAM utilizes capacitor as storage cells, which are made from silicon and are very small in size. As a result, they tend to lose the voltage over time, which is referred to as the dynamic nature of DRAM cell. To maintain the logic state of the liquid DRAM cell, the state would be reached before the charge dissipates completely, then written back to restore the charge to a full, freshly written state. This process is known as refresh. To address this issue, DRAM uses a special type of read then write cycle known as refresh that updates the charge state of multiple cells at once, usually one or more of cells at a time, which account for about 1 over 256 of the DRAM. The refresh operation in the array against time seen on the DRAM row must be accessed before the content dissipates completely. Typically, the time required to hit on the row range between 8 and 16 milliseconds. How does DRAM refresh work? While the memory is in operation, it is necessary to periodically refresh a memory cell within a specific time frame specified by the manufacturer, typically in the millisecond range. This refreshing process differs from the regular read and write cycle used for accessing data. Instead, specialized refresh cycles are generated by dedicated counter cycles within the memory circuitry and interleave between regular memory operations. Memory chip consists of storage cells arranged in rectangular grids of row and column. The read operation in DRAM is destructive, causing the charge in entire row of memory cell to be lost. The temporarily preserves the data. The chip includes the row of specialized large column called the send amplifier, with each column having its own send amplifier. During a normal read operation, the send amplifier read and writes the data, followed by the rewriting the data in the access row before transmitting the bit from a single column as an output. This allows the chip regular read electronic to refresh an entire row of memory simultaneously, significantly expediting the refresh process. Also, a regular read or write cycle refresh a row of memory. It cannot guarantee that all row will be refreshed within the required time frame. Hence, a separate refresh process becomes necessary. Instead of using the complete read cycle for refreshing, a condensed cycle called refresh cycle is employed to save time. The refresh cycle resembles the read cycle but executes faster due to two reasons. It only requires a row address, eliminating the need for column addressing in the chip circuit, and the data read from cell does not need to be passed through output buffer or data bus to reach the CPU. The refresh circuitry must perform a refresh cycle on every row of the chip within the designed refresh interval to ensure that each cell is equally refreshed. The last is the reference.